Hi guys, greetings of the day. Myself Raghu. Today I am going with design of spur and helical gear, 10th part. In the previous one, we went through beam strength of helical gears, dynamic load, endurance strength, and wear load. This part will start with the procedural steps for the design of helical gears. So how to solve the helical gears? What are the procedures are there? We will go through that one. The first step is identify the weaker member. So almost all the procedure of spur and helical gears are similar only. So very small changes are there with respect to equations. Remaining thing will be same. So coming back to this one, identify the weaker member. To identify the weaker member, first we have to draw a tabular column. So first column it is a particulars. Next sigma naught y sigma naught into y remarks. So another two rows will come, one for the pinion and another one for the gear. For pinion it is sigma naught 1, gear it is sigma naught 2, y it is y1 and y2, and this one is sigma naught 1 y1, this is sigma naught 2 y2. Here sigma naught 1 and sigma naught 2 are called as the allowable static stresses. If in the problem statement if they have given, we have to use that one. If they are not given sigma naught 1 and sigma naught 2, we will get these values in table 23.48. For the given materials using table 23.48, we have to get sigma naught 1 and sigma naught 2. So y is nothing but that is y1 and y2 are the Lewis form factor for pinion and gear respectively, and it has to be with respect to formative number of teeth. For the given normal pressure angle and tooth form, we have to get this y1 and y2. So we have the equations for y1 and y, that is y is equals to 0.124 minus 0.684 divided by ZV. This is for 14.5 degree involute. The equation number is 23.115. In the data handbook, it is not with respect to ZV, it is with respect to Z. Next, y is equals to 0.154 minus 0.912 divided by ZV. This is for 20 degree full depth involute. This equation 23.116. Next, y is equals to 0.17 minus 0.95 divided by ZV. This is for 20 degree stub, and this equation number 23.117. So depending upon system of gear, we have to use the y equation and we have to find out. Here ZV is called as the virtual number of teeth that can be calculated with the help of Z divided by cos cube beta. So equation number 23.285. Beta is nothing but the helix angle. Z is the actual number of teeth. So by calculating y1 and y2 and multiplying these two, second and third column, we will get the fourth column. So whichever value is lesser out of sigma naught 1 y1 and sigma naught 2 y2, that will be the weaker, and design should be based upon weaker member. This is the first step. Second step, design based on model in normal plane it can be denoted by mn as standard model. So in this one, first step, there is a tangential tooth load. We have the equation for tangential tooth load, that is Ft is equals to 9550 into PCS divided by N into R. Equation number 23.87b. So here P is nothing but the power. They will give you in the problem statement. N is the speed of the weaker member. That one also they will give you in the problem statement. R is the radius of the weaker member, that is equals to d by 2, which is equals to mn into z divided by 2 cos beta. And CS is the service factor. We will get this CS from table 23.13. By substituting all these things, we will get Ft, and we have to call this as equation number 1 afterwards. Next, B, tangential tooth load from Levy's equation. We have the equation, Levy's equation, that is Ft is equals to sigma naught by Pt Cv cos beta divided by Cw by modification, which can be written as sigma naught by Pn Cv divided by Cw. Equation number 23.286. Sigma naught is the allowable static stress of the weaker member. Y is the Levy's form factor for the weaker member. B is the face width that can be assumed within the range, that is Pt by tan beta should be less than B, which should be less than 28 mt divided by tan beta. So this one we have in equation number 23.277, and this one higher value for B we have in 23.280. By modification, substituting the values, that is Pt can be written as Pn divided by cos beta into tan beta should be less than B, should be less than 28. MT can be written as Mn divided by cos beta into tan beta. So after modification, we will get it as Pn can be written as pi Mn divided by sin beta less than B less than 28 Mn divided by sin beta. So within this range, we can assume the B and we can substitute in this equation. Then Pn is nothing but pi Mn. Cw is the wear and lubrication factor. We will get this Cw from table 23.47. Then Cv is called as velocity factor. That depends upon the mean pitch velocity, that is Vm. So Vm we have to calculate, that is pi dn divided by 60,000. So d is the diameter of the weaker member, n is the speed of the weaker member. By calculating this Vm, depending upon the Vm, we have to use the Cv equation. So we have three different equations for Cv. So when Vm is less than 12.75 meter per second, then Cv equation can be written as 4.5 divided by 4.5 plus Vm. This is up to 12.75 meter per second. Equation number 23.288a. Similarly, if it is more than 12.575 meter per second till 20 meter per second, it is Cv can be written as 6 divided by 6 plus Vm. This is up to 20 meter per second. So equation number 23.289a. And if it is more than 20 meter per second, we have the equation Cv, which is equals to 5.6 divided by 5.6 plus square root of Vm. This is over 20 meter per second. Equation number 23.290a. So based upon the Vm value, we have to use the Cv equation and we have to calculate. By substituting all these values in Ft equation, we will get some value for Ft. We have to call that as equation number 2. By equating equation 1 and 2, we will get module Mn by trial and error method. So once we get the Mn, we have to check for the stresses. The third sub-step, that is C, is check for the stress. So we have to calculate sigma induced and sigma allowable. So sigma allowable is equals to sigma naught Cv allowable. Yes, sigma naught will be the allowable static stress for the weaker member, and Cv is the velocity factor when the condition satisfied. At that time, whatever Cv will be there, that value you have to substitute, and this is the sigma allowable. Similarly, sigma induced is equals to sigma naught Cv induced, which is equals to Ft into Cw divided by Bypn. In this one, Ft is the tangential tooth load. In the substep A, whatever we calculated, that one we have to substitute. Cw will be the wear and lubrication factor, that one we have to substitute. B is the assumed phase width, that one. Y is the Lewis form factor for the weaker member, that one we have to substitute. And Pn is nothing but pi into Mn. By substituting all these things, we will get sigma induced. So always sigma induced should be less than sigma allowable. Then only we can say the design is satisfactory. If it reverses, then we have to increase the model until this condition satisfies. This is the second main step. Third one, dimensions. So we will get the dimensions from table 23.1. So along with that one, we have to calculate center distance, root circle diameter of pinion and gear, and addendum circle diameter of pinion and gear. And in the fourth step, checking. So in this one, a dynamic load. We have the equation for dynamic load, that is Ft is equals to Ft plus 21 Vm into Ft plus Bc cos square beta into cos beta divided by 21 Vm plus square root of Ft plus Bc into cos square beta. Equation number 23.309a. So Ft is the tangential tooth load, Vm will be the mean pitch line velocity, B is the phase width, beta is the helix angle, and C is the coefficient. That coefficient we will get from the error, small f. Error f can be calculated with the help of either figure 23.34a or from figure 23.35a. So 34a we are using when we know the class of gear. If we don't know the class of gear, then based upon Vm, that is velocity, we can use figure 23.35a to find out error f. Once we find out error f from table 23.32, based upon this error f, we can find out C. By substituting all these values in this equation, we can find out Fd, that is dynamic load. B, endurance strength. We have the equation for endurance strength as Ff is equals to sigma f b capital Y mt cos beta. That is equation number 23.293. By modifying the equation, we will get sigma f into b pn y. B is the phase width, pn is nothing but pi into ml, and y is the Lewis form factor for the weaker member. By substituting all these things, we will get Ff, that is endurance strength. Last step, that is wear load. So we have the equation for wear load. Fw is equals to d1b qk divided by cos square beta. Equation number 23.310. So d1 is the diameter of the pinion, b is the phase width, q is the ratio factor, which is equals to 2z2v divided by Z1V plus Z2V, which is equals to 2Z2 divided by Z1 plus Z2. K is the load stress factor, which is equals to sigma FAC square into sine alpha n divided by 0.7 times of E naught. Equation number 23.311. E naught is the equivalent Young's modulus, that is equals to 2 E1 E2 divided by E1 plus E2. So E1 and E2 are the Young's modulus of pinion and gear respectively, whereas sigma FAC is the limiting stress for surface fatigue, that is equals to 2.75 times of HB minus 69. Equation number 23.294a. By substituting all these values in FW equation, we will get the wear load. Always FW and FF should be greater than FD. Then only the design is safer. If FW is less than FD, then we have to make one or more changes, that is calculating the error small f or calculating FD by decreasing error small f. Then second one is decrease the module Mn. Third one is increase the face width B. And fourth one, increase the surface hardness. So either one or more changes we have to do until FW is greater than FD. This completes the design procedure. Thank you. Please subscribe my channel.